let us begin. So we're right in the middle of this problem, trying to understand what a Bayesian does to test this sharp hypothesis. I want to point out before proceeding, you'll see this in examples, but a Bayesian really is thinking about this hypothesis quite a bit differently than in the classical framework. Classical framework is literally asking this question: is theta theta not? And the reality of the situation is it's probably not. And so they want to be able to tell within some epsilon whether or not that's true. That being able to tell within some epsilon and getting a sample size that does it, maybe that's a good way to do it. So doing the formal power analysis, seeing what n needs to be to see that my type 2 error will be sufficiently low with the fixed type 1 error of alpha, maybe that's a good way to proceed. But I will warn you that if you don't have a good coherent stopping rule, like based off of power analysis, if you just continue to collect data in your classicist and you're doing the typical p-value calculation, your p-value will duck alpha eventually, no matter what, probability 1. So if the alternative is true, then the p-value is getting smaller and smaller and smaller. So the probability of more extreme data that you saw given the null hypothesis, basically the standard error is getting really, really tiny. It's getting tinier and tinier and tinier. And so that z-score is going to get bigger and bigger and bigger. There's a fixed distance between true theta and theta null, i.e. x bar, which estimates true theta, and your hypothesized value. And so that z-score is going to be getting bigger, and you'll reject under the null hypothesis, or under the alternative hypothesis. Under the null hypothesis, a p-value is uniformly distributed. And somebody asked me that last week. I've asked you to show that on your homework. There's a couple different proofs that you can consider, but really it's the exact same proof to the inverse CDF thing. You just want to think about what a p-value is. It's the cumulative distribution under h naught. So like this thing, fx under h naught, that's the cumulative distribution. I want to see what the distribution of this creature is. So this is your p-value. How do I do it? I check the measure that I think is creating the data under some other hypothesis. So, and I want to check to see if this is less than some value. I'll call it t. Okay? I'm going to call it happy face, just any old value. And so, under some other hypothesis, I'll call it hypothesis I. So what happens right here, this is a CDF, so I can invert it, because CDFs are monotonic. They're always increasing. And so, here's one such proof. So T, F, H naught, inverse T, given HI. Kind of written this under h naught. I'll write it over here. If this h naught, these are the same hypotheses right here, then this is the same function. So this would just be f inverse t. If they're the same hypotheses, under h naught, same function. What's that thing? It's t. So what's the probability of a random variable being below t and its t? Only uniforms do that. And I probably have to specify my range, only goes between 0 and 1. This is kind of the easy proof that you'll see in most textbooks. I always like you to think about very clearly what happens when this is the alternative. So that's a little bit more insight as to how fast is that p-value decay as a function of n. I'll have you play around with this type of concept on the homework.
It's uniform, right?
It's uniform. Probability of something is less than that thing, it's uniform. There's only one thing that does that. So when I say what's the probability of the uniform being less than 0.7, it's 0.7. It's the probability of uniform being less than 0.3, it's 0.3. So only uniforms do that for obvious reasons. Okay, so if a classicist is testing this hypothesis and the null is true, you're just generating this autocorrelated uniform. It's a function of the sample size, so that thing's just going to hover. And eventually it's going to be less than alpha. How often? Alpha, because it's uniform. So 0.05% of the time, 5% of the time. So it's the typical sort of thing. So we should see built into science, if we're following the classical regime, that 1 in 20 papers are not right. So they just discovered those results by chance. That's kind of built into the standard. A Bayesian has a very different feeling about this sort of thing. They're not testing this, because they kind of know what's going to happen if n gets really big. So people find a lot of stuff and claim a lot of things when they have big N, probably because their null model is incorrect for reasons other than just the hypothesis, probably the model is wrong. So the Bayesian is really asking, are you close? And close is going to be governed by this alternative distribution in the prior. And so I have mass on the null right here. That's how much mass I'm going to put on there. That's how much mass I'm going to put on the alternative. And this is how I'm going to smear mass all over the alternative. This is how I smear mass on the null. There's only one choice because I'm testing at a point. If the null was a continuum, then I would have to smear mass all over that thing. So really, Bayesians are doing some sort of weighted average, and how they average has to do with this weighting function. How much mass am I putting in different places in the alternative compared to the null? And so we are inclined to maybe choose a normal distribution because it's the easiest thing we can do. It's the conjugate prior, and at least I can work out the math. I will say there's repercussions to doing this. I'll allude to them in a moment, and I'll talk more about them next week. But for good reasons, we thought maybe we should center it around the null. Otherwise, why are we testing the null? I wouldn't center it, if this thing was 0, I probably wouldn't center this at 10,000. Doesn't make any sense. So I'd probably put it somewhere symmetric around the null, if I wanted to test each side equivalently. And then I've got some variance. So this is the major culprit in all of this. We'll have to keep our eye on that thing. But this assumption normality, if you just kind of draw what this prior looks like, it's a normal centered at the null, and then I have a point mass also right in here. And so the alternative is certainly stacking mass around the null. And the repercussions to doing that are the rates at which you'll accept the alternative and the null as a function of n. So I'll just shout out the result, that when you work through everything and you get the posterior probability of the null, that's what the Bayesian wants, is the posterior probability of the null given the data. If the null is true, you'll support that exponentially fast as a function of n. Okay, so I'll climb to 1 exponentially fast. And that's because the alternative puts so much mass right around the null. Turns out it's a little bit lopsided, this analysis. And if the alternative were true, as a function of n, I want to see the posterior probability of the alternative converging to 1, probability of the null converging to 0, it does it linearly fast. And so that's the repercussion of this. So there are other forms of these priors that you can pick to try to match those rates a little bit more equivalently. And so I think that that's something that should be considered. Of course, being that this is a Bayesian contraption, there's lots of argument surrounding what should you do. And so fierce, heated debate. I'll talk about this form, but I think at least in the limits it does the right thing, the speed at which it does it, we might be able to tailor. I'll talk about those issues next week. But basically a Bayesian is going to be asking, how close are you to the null? And this is measuring close. Okay, so lots more I need to say about all this. I want to point you in the direction of a textbook that I find peculiar. As long as this is on Amazon, I'm going to keep pointing to it. I found this on Amazon when I was in graduate school, 2006. So as long as Professor Dytham is selling this book, I'm going to point to one of his passages here. So Calvin Dytham is a biologist. He's a professor at York University. And he wrote a book on statistics. So we see a lot of people out there peddling statistics and statistical analyses in other fields other than statistics. So good on Calvin for taking all this knowledge and reaching out. So Amazon's pretty cool. They'll let me look inside this book. And so I'm just going to click through it a little bit. He's got some stuff in here. Let's just click to the beginning. He has a glossary. And so I like glossaries. It's like, let me know what the terms are. Explain them to me. And he has a passage on p-values. And so let me just read this to you real quick. The p-value is the bottom line of most statistical tests. Yeah, I think that's true. Unfortunately, it is. So most statistical testing is done using a p-value. So the p-value is the bottom line of most statistical tests. Incidentally, you may come across it written in upper or lowercase, italic, or not, e.g. p-value, 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 p-value. Way to go, Calvin. So it is the probability of seeing data this extreme or more extreme if the null hypothesis is true. So I'm okay with that. You will hear people fight against this language also, given, fixed value, the null distribution. It's all the same to me. So again, I'll read. It is the probability of seeing data this extreme or more extreme if the null hypothesis is true. So if a p-value is given as 0.06, it indicates that you have a 6% chance of seeing the data like this if the null hypothesis is true. In biology, it usually takes a value of 5%, 5% a critical level 4, 1 in 20 chance of being true if we reject it. As it is the null hypothesis that is nearly always being tested, we are always looking for low p-values. So let's go on and read this. I'm actually a little bit concerned. So I read this in my inference class last year, right? You guys remember this? No? Sierra, you've seen this. They've actually fixed this. Let's read this. A p-value of 0.0001 indicates that if a null hypothesis is true, the chance of seeing data as extreme or more extreme than that is being tested is 1 in 10,000. This is all right. So I'm kind of amazed. I should have looked at this before walking in. So, and Calvin, bravo for fixing this. He used to say something different. He used to talk about the probability of the hypothesis being true, given you've observed that data. And that is not what it is. So it's taken over a decade to fix this passage. In here, I wish I had now an archive of it, but sometimes p-values are misinterpreted. So I'll point out that Calvin has done a very good job in his explanation. I agree with that. So Sierra, do you remember this being written differently once upon a time?
Yeah,
So,
I don't remember the exact words, but
yeah,
I remember
either,
it sounding really weird.
I'm going to say he's fixed it. That's okay. I'll see if I can find an archived version of this later, just to make sure you know that he used to say something different. Anyway, don't ever let anybody tell you that a p-value is the probability of the hypothesis being tested. That's what a Bayesian's doing. So they're applying this prior to this likelihood function that's induced from this sampling distribution, and then they work out what the probability of the null is given the data. It's unfortunate that I didn't have a good punchline with all that. I do have homework up as well. Maybe we'll look at that just real quickly so you can see what you're getting into. I'll have this posted very soon after class. So problem 1, I want you to basically look at the same regression model that you played around with last time, and I'm going to ask you to actually implement the Gibbs sampler. So some of you wrote it down a little bit wrong, the Gibbs sampler, and so just keep in mind that all the forms that you're using are the least squares, weighted least squares regression forms. And if you don't recognize that in all your solutions, it's because you didn't do it correctly. If you need some help on working out what these full conditionals are, I can help you. But you're going to have to learn how to do that before you can actually implement this thing. So I want you to write down the full conditionals. Yes, again, I know you already did it. I want you to sample from a bivariate Cauchy with correlation structure that I'm writing down. This isn't correlation structure, but it's like that scale. So, matrix. And then I want you to implement the Gibbs sampler for inferring beta and phi. You will have to infer all the gammas as well, but I don't really want to see all of those. and I want you to demonstrate that this thing works. So that's it. Basically just implement what you wrote down last time. Problem 2 is a little funny. And so I want you to generate some data where I've got 400 of the x's, 200 of the x's, 300 and 100. Those add up to 1,000 of them coming from different means in this model. So essentially you're sampling from a mixture model. I didn't flip a coin to generate what the ends are. But if you didn't know what they were, you would assume that maybe it's a coin flip and you'd try to estimate that. So what I want you to do is play around with a couple different hypothesis testing techniques, this one and the typical p-value thing. And I want you to test sequentially these hypotheses. Theta is equal to 10. This is not true. So the model that generated the data is a mixture. And so I want you to do some testing under incorrect models and see what these things do. So I'm going to ask you to compute the posterior probabilities for these 4 different hypotheses that I could pick. So theta is equal to 10, 15, 17, or 20, and compare them to the other things. Keep in mind the alternative space when you do this test, it's only being evaluated at 3 points. It's not continuous. Okay, so the alternative would be a point mass on 3 different locations, and the null would be a point mass on 1 location. How am I going to weight those 3 different point masses? Probably with probability 1/3. So my overall prior for doing this, so I asked you to write down the appropriate prior, I'll just tell you what it is. It's 4 point masses, each with uniform probability on it, 1/4. And so I want you to write down the Bayes factor for testing each of these hypotheses. You'll notice that you'll need to take probably a logarithm of sums of things. We talked about that a couple weeks ago to try to figure out how to do that. There is a numerical issue that appears in this problem, and it's your task to solve it. So I want you to randomize all the x's, and then I want you to compute a Bayes factor or the corresponding posterior probability of the null hypothesis is a function of n. So I want you to show what the pH naught given all of your data. And I want you to show what that posterior probability is doing. Keep in mind, the 4 posterior probabilities, if the data is ordered exactly the same, should add up to 1. So, okay, Bayesians are coherent. I want you to do the same thing and compute the p-value sequentially and show what it does. And then I want you to code up the whole mixture model and do what you're actually supposed to do in a problem like this. So I want you to see how both of these contraptions, p-values, posterior probabilities, work when the model's wrong. And I want you to actually do the right thing. So most of your work is in this part H, using reasonable priors. So I want you to get to a point where you can say what the priors are that you should be using. Implement the Gibbs sampler for sampling the posterior probabilities of these things. Posterior distributions of these things. So I don't see this really as a hypothesis testing sort of question. It's really estimate the model. And so that's what I always try to talk people into. Since there's such a divide in hypothesis testing, it's really out, what do you really want to do? Let's estimate something and I'll tell you what it is. Kind of a different mindset. And then I want you to work through some calculations, computing these posterior probabilities of H naught, and we'll have you do it in the binomial case. You just have to write everything down. Prove under the null hypothesis, the p-value is uniformly distributed. I just did it for you. That's one such proof, but maybe think a little bit harder about it. Okay, so homework's out. Okay, let's get back to Bayesian testing. Any questions before I carry on? Any questions from seminar yesterday? About half of you went. You guys all understand what he did? You could do it? No. So, we've got a few more weeks in this class, so if there are topics that you guys are interested in, and I saw a whole bunch that you guys probably don't know much about, get thrown out yesterday. You can cover some of that stuff. Okay, so let's get back to this problem. So we want to do this test. So the Bayes factor I can compute that. Bayes factor is just this thing. Integral of my likelihood given my data. I'm going to use x bar because it's sufficient for inferring theta. And then I'm going to multiply by my prior distribution, i.e. theta is equal to theta naught, how I smear mass over the null hypothesis. And I'm integrating only on that point mass anyway. Divided by integral likelihood, x bar. And then I've got my prior on how I smear mass. So I'll just write this thing down. This is going to be 1 over 2 pi square root psi e to the minus 1/2 theta minus theta naught squared over psi squared d theta. Keep in mind, we don't see cancellation here in these things. These constants that we've been able to throw away throughout analyses might not just disappear in our analyses now. There's some real repercussions to that. But a lot of cancellation in numerators and denominators, and estimation was easy. That same cancellation we usually don't see in hypothesis testing. So I gotta write this stuff down, get it all down there. And so what does this thing look like? Well, any sort of constants in the likelihood, they still cancel each other. So I don't have to worry about those ones, but in my priors I do. So what does this thing look like? I could just write it down like this. So 1 over sigma, could put the 2 pi's in there, they'll cancel out. So e to the minus 1/2 theta minus x bar squared sigma squared over n. Same thing up here, the sigmas will cancel each other because I'm saying that they're known. And so I need to solve these two integrals and form this Bayes factor. So I want to write down this Bayes factor and analyze it. What does it do? So there's good rationale for thinking that maybe the Bayesian has some solution to this hypothesis testing problem. So this thing, it's real easy to write down. It's just going to look like this. I'll get rid of the sigmas in here so I don't have to just write them down, but this is going to look like e to the minus 1/2 theta naught minus x bar squared over sigma squared over n. So that's the numerator. Denominator is a little harder to work out. So I just want to point out that this part right here, we could write it down like that. Px bar given theta, and then this is going to be pi theta, our prior on HA. So, and this has, it's centered at theta naught. It has variance psi squared. So this also has variance sigma squared in here. And so if you want to think about this thing right here, it's px bar under the alternative. So it's the margin of the data.
Why is it that we don't use pi sub 0 in the numerator?
Bayes factors have those priors taken out of them. They
Right.
don't appear in the Bayes factor. The posterior ratio has them, but the Bayes factor has them canceled out. If you remember that one expression. It turns out it's equivalent to just these margins. So I'll write this down just a little bit differently for you. The Bayes factor is P under H naught of the data. If you want to write that a little bit differently, I can do that. This is usually what I mean. H naught. If I wanted the posterior probabilities of everything, I need the pi naughts, the 1 minus pi naught down here. So again, the Bayes factor is just the margin of the data under the two hypotheses. Remember, we picked how to weight the hypotheses through our priors. So we're comparing two weighted averages. That's all a base factor is doing. So base factors, people will say things like they're prior free. My prior doesn't appear there. And it sounds pretty good. So they're not influenced by my prior. It's total hogwash. So it doesn't have pi naught, but how you smear mass in the spaces certainly matters. So don't fall for these things that people say. Sounds good, it gets you out of debate real quick, but might not be true. And then this part right here is just this integral of px bar given theta, p theta. I'll write down sigma squared right here, theta naught psi squared. Call that a pi. Cool. Does anybody know what this integral is? Remember, this is just px bar under a. So in a lot of my classes, I have people solve this integral over and over and over and over, and you've already solved it a couple times in this class. You didn't do it in the same context, but you certainly integrated over two normals. How did you do it? You completed the square. So does anybody remember from all that hard calculus that you did? Completing the square, oh my goodness gracious. Fouls so many, graduate students up. So undergrads can't be messed up by that, but when you get to graduate school, this is a hard calculation. Does anybody remember what it is? It's worth remembering. So this is going to be some distribution. What distribution do you think it is?
T.
When you integrate out sigma squared, it becomes a t, but if you know sigma squared, it's going to be a normal. So that integrating, that extra term in completing the square pops out of this, and it's going to be e to the minus some quadratic form. So it'll be a normal. Which normal is the question? What do you think? Where do you think it's centered? Just guess. Theta 0. Where else is it going to be centered? So it's true. It's centered at theta 0. And what do you think the variance is? It's bigger than sigma squared? Probably, right? You're including more uncertainty through this averaging process.
Is it the sum of sigma squared plus 1 over psi squared?
That would be weird to mince a variance and add it to a precision.
Is that, it's not the precision, okay, so it's sigma squared plus,
Yeah, this
so it's
is,
the sum of the two of them.
yeah, probably. Sigma squared over n plus psi squared.
Yeah, that's right.
You want me to give you a little mathematical sleight of hand? It only works for this problem, but it might give you a way of remembering this. So somebody can tell me where my mathematical sleight of hand is. That's true, right? No mathematical sleight of hand. This is pretty true. Okay, so I'm just going to look at this real quickly. I know the distribution of this thing, and I think I know the distribution of that.
That's
Okay.
why it's the sum, right?
So x bar minus theta, I've got what normal distribution this is right here. So x bar has mean theta. So x bar minus theta has mean 0, right? Okay, so this thing is normally distributed with mean 0 and variance sigma squared. I didn't change the variance of this thing. Sorry, over n. What's the distribution of that? It's my prior.
It's also
I chose it to be normal for my own convenience.
centered
So
at theta 0,
centered at theta 0,
psi squared.
psi squared. I'm adding those two random variables together. What is this thing?
Also a normal.
That's a normal. And what do I do when I add two normal random variables together? I add together their parameters. So theta naught, sigma squared over n plus psi squared. Now I'm going to get a revolt from you for doing all that. It's in Jim's book. It's in this book right here. I thought it was really cool when I read it. I was like, you can't do that. That's nonsense. Why is that nonsense? It looks pretty good though. It'll probably help you to remember when I have two normals and I integrate them, what is it? I'm getting a margin. I want this distribution right here. And so, because I treated this one as random over here and that fixed, and then I made that random. So if you don't like it, please don't come and like spray paint my office and stuff like that and protest. It's just a tool that can help you to remember. Jim said it, so it must be a good thing in his book. It's not true. So, but anyway, it'll help you to remember those normal integrals, what's going on with them. Okay, but your intuition was pretty good. You got the right thing too. So just by thinking about it or trying to remember it. The real way to do that is just do it once and remember what the result is, go through the exercise. But this is going to be a normal, beta 0, sigma squared over n plus psi squared. So our Bayes factor looks like this. Bayes factor I can write down and I can do it analytically. That's the beauty of a conjugate prior, but these rates I kind of find a little bit unenchanting, so I might want to use something different, but at least we can do the hand calculation in class. Any other prior I picked, I probably couldn't do this on the chalkboard. So my Bayes factor is equal to, I'm going to write it down a couple different ways, so I'm going to simplify it for us. It's going to be, well, I'll just write down sigma squared over n minus 1/2. So what I'm doing when I do this is I've written down all of my normalizing constants in both of them. So I did have my sigma squareds when I write this down. So this is going to look like e to the minus 1/2 x bar minus theta naught squared over sigma squared over n. So this is just the likelihood function. I'm plugging in theta naught, and I did keep my normalizing constant in front of here. Divided by sigma squared over n plus psi squared minus 1/2. I got rid of my 2 pi's and all this stuff. E to the minus 1/2 x bar minus theta naught squared over sigma squared over n plus psi squared. So I could have just written that down from what we had before. I kept my sigma squared down here. It gets added to that one, so I did have my sigma squared appearing, so I had to include it in the numerator. Just makes everything work out a little bit nicer. This is a disaster to look at. So I'm going to do some simplification. So I'm going to write this differently. And if you're so inclined to see the algebra, I do have it all right here, but I'm sure you can do all of this. This thing is going to be equal to this. 1 plus psi squared n over sigma squared to the 1/2, that's positive, e to the minus 1/2. What do I want to write down? We'll write it this way. X bar minus theta naught squared over sigma squared over n times 1 plus sigma squared over n times psi squared inverse, obviously. So they're the same things, just rewritten. So I just combined everything into the exponent. And the interesting thing to notice is this is a very typical statistic that we're used to looking at. So this was written this way. This is all from Jim's book, so that we could isolate this quantity. What do we normally call that thing? It's the z-score. It's the z-score squared. So this is z squared right here. And so the Bayesian's calculation does include the z-score. The classicist calculation only uses that. So this is some sort of penalized form of the z-score right here. I want to show you what happens as a function of a couple of these arguments in the function. Here. So if we ended up letting, I'm going to plug in some numbers right now, pi naught. I'm going to let that be a half. We thought that was pretty reasonable. I would typically pick a half. And since we know sigma squared, somebody said, why don't you just use it? And so what I'm doing when I choose this is I'm saying my prior is worth one data point of weight. And so maybe that's a reasonable thing to do. That was your suggestion, right? If you know sigma squared, just use it. Okay, so I think maybe that's a reasonable thing to do. I'm going to say n is equal to 15. And I'm going to let z be equal to 1.96, or a good old friend. And see how this varies as a function of z being equal to 1.96. And so, quick question. What is the corresponding p-value for testing h naught? I think I just answered this.
You mean from a classical perspective, if we're going to use that z?
Yeah, that's what I mean when I say p-value.
Okay.
So
0.05. Yeah, absolutely. 0.05. And it wouldn't have mattered what any of these things were. It just matters what that is. So the posterior probability, so I'll just write down probability of h naught given x bar is going to be equal to 0.04. How do I, 0.4. So how did I get this? I took my Bayes factor and I did something to it. So my posterior probability, h naught, given x bar, is going to be equal to 1 plus the prior odds inverted, Bayes factor inverse, all inverse. This is Bayes' theorem in disguise. If you just expand out all the terms, you'll see that that's the posterior probability result. So all I did is I computed this Bayes factor. I believe this ends up becoming in our calculation because I picked this to be a half right here. This cancels out. I believe this is this. 1 plus 0.66 inverse inverse. And that becomes this value, 0.4. So the Bayesian and the non-Bayesian feel quite differently about this data. Let me show you, as I change a few more of these parameters, what happens. So I'm just going to let n vary here. So again, z is going to be 1.96, pi naught is a half, and sigma squared is psi squared. So as a function of n is equal to 5. Show you a few of these. 10, 100, 1,000. So 0.331, 0.367. Got a 50 in here as well. 0.521. This is 0.6 and 0.823. So the probability, if I ended up seeing all of these things and I just changed n, I feel very differently about this hypothesis. What's going on here? Is this reasonable? What do you think about the Bayesian's result? So as I vary n, if I ended up seeing z as 1.96, fixed value, I had these hyperparameterizations. My prior odds is 1. Pretty reasonable. And I let n increase. I feel very differently about that z-score. Do you think this is reasonable behavior? Do you like it? It certainly says there's a huge conflict between what a Bayesian and a classicist think about everything. Can you think of any argument that says maybe this probability should be going up as a function of n?
As you have more data, you are more certain about something, right?
That's true. That's always true. So maybe I'm more certain about the alternative though. So why should it be increasing? Any argument on that?
So this is a fixed 2 standard deviations out, almost.
We did this. This is how we started our argument. We looked at this score, Zn, x bar, minus theta naught, absolute value, sigma squared over n. This was a function of n as well. As n goes to infinity, that's going to 0, which means that this must be going to 0 if this thing is 1.96 as a function of n. What is x bar going to? That's going to theta. This thing's staying at theta naught. This thing's going to 0, so theta must be going to theta naught. So with probability 1, in the limit, I believe that theta's really close to theta naught. How far away is it? Well, on a relative scale, it's still 1.96. But if I just look at it on absolute scale, it's epsilon. If you don't like how small my epsilon is, and you want it smaller, just increase that and you'll get there. So I think theta is so close to theta naught that I wouldn't be willing to reject it with respect to psi squared, how much mass I put other places. But how close is theta to theta naught? Really, really, really close if z is 1.96 in the limit. So that's my point. I think the Bayesian's asymptotics are reasonable. And so if I don't see this in people's hypothesis testing and they're testing at a point, I've got a real problem with it. Now, classicists will still say I'm just looking for standard deviation. How many standard errors am I from the null? Still 2. I think they're different. They're right. So it is different. It probably is. But it's so close that I don't care. So the question is what does a human want? Do they want to know something is exactly theta naught, or do they want to know if it's close? And I think the question is it close? So everything we do in statistics land is an approximation. So nothing is absolutely certain. And so I can answer the classicist question for them. All these tests that are going on all over the university, is theta theta naught? I've got the answer for all of them. It's not. So it's something different. It might be really close though. And so I think that this is reasonable behavior right here. I want to show you something else. If we look at this quantity right here, what happens as psi squared goes off to infinity? What does the base factor do? Goes to infinity. So what is the posterior probability of the null go to? Goes to 1. So the base factor will go to infinity. What you have to do is look at this thing. Thing's becoming 1. This is just a fixed value. And this thing is flying off to infinity. So this is converging to something, and this is going to infinity. So it's going to infinity. If I plug in infinity into this thing, infinity inverse is 0. 1 inverted is 1. And so the base factor goes to infinity, and the posterior probability of h naught is going to go to 1. And this is true in general. So if you're testing at a null and you use a flat prior or something really diffused, you're going to be upping the weight on the null. And that's wildly unsatisfying to me, because a lot of times I don't know what to do with psi squared in general. Maybe I know sigma squared. Maybe I use some data and I try to estimate it. So those are called intrinsic or fractional Bayes factors, where you use a minimal training set to try to calibrate that thing. And there's a whole bunch of different suggestions. You got a question? Question?
I had something, but I got distracted.
Okay. Let me conclude with some remarks. So this is from Jim's book. I'm going to talk more about this. Some people will discuss this problem as the Lindley-Bartlett paradox. The Lindley-Bartlett paradox really refers to the gross disagreement between people that are testing with a p-value or being a Bayesian, who just do not agree with each other on how this stuff is supposed to work or what the answers are supposed to be.
I remembered.
You remember, Ben?
Yeah.
What you got?
So if you go conversely, psi squared goes to 0, then the probability of the null will also go to 0.
Yeah. So you can look at this thing, you need a well-calibrated sigma. So it's kind of interesting. What it will really do is if I ended up putting a point mass somewhere else, so if I ended up putting the point mass at the same place, posterior probability of the null and the alternative aren't discerned, and I'm asking a bogus question. Is it that or that? And they're exactly the same question. So you should have fundamental breakdown because you asked the wrong question. What will really happen in this is if I centered the alternative somewhere else and I put a point mass on it, what it's going to do is, as a function of n, it's going to end up going to 1 on the hypothesis that x bar is closest to. So what you're really asking in the Bayesian land is, out of my whole universe of hypotheses, which one is closest? And that's what's going to happen in your homework set, where you have the 4 hypotheses. The Bayesian, as a function of n, is going to say it came from the one that's closest, but you've given me my whole universe to consider. So you've set up the question wrong. The p-values will all go to 0. It'll tell you the right thing. None of those are right. So what should you do in these cases? Use the right model and estimate it, I think. Let me read a passage from Jim's book. So Jim Berger, esteemed faculty member at Duke University, he wrote this book on statistical decision theory. A lot of Bayesians got persuaded to be Bayesian because of the decision theoretic aspects. Really, the aspects of averaging and averaging properly have good properties on average, you know? And so it makes sense. Okay, the conflict in the above example, so this is exactly the same example, is of such interest that it deserves further investigation. The Bayesian analysis can, of course, be questioned because of the choice of prior. The assumption of a normal form for G can be shown to have no real bearing on the issue unless x bar minus theta naught is large. It can have issue. So it's just, you got to look at when this book was written, and they couldn't do anything else. So compared to all the other things that they were willing to do at the time. And so I think it does have issue. And the choices of your centering parameter being theta naught and pi naught being a half are fairly natural. Indeed, if we're trying to be objective, these choices of the centering parameter and the prior, pi naught, would seem to be virtually mandatory. I kind of agree with that. One could certainly question the choice of plugging the variances together in all of this. However, Jeffries in 1961 argues for such choice in objective testing, but the answer definitely depends crucially on the choice of the variance. Jeffries actually prefers a Cauchy form for the prior. But again, the form matters only in extreme cases. I think most cases we see are reasonably extreme, especially with respect to n and what the standard error is. When you say something is large, you always need to say, compared to what? It's compared to the standard error, so this is a function of n that he's talking about. I do prefer the Cauchy tails. I think that it has nice properties, and I don't have to think so much about the scaling parameter because I still have mass way over somewhere. You've experienced the Cauchy and you've kind of felt that phenomena that even though it looks like the tails are coming down pretty fast, there's tons of mass under the tails. And so I like that. I like to do something else to this prior as well, but I can't do the hand calculation anymore. Jim concludes by saying, when the answers heavily depend on features of the prior, such as the variance, Bayesian has no recourse but to attempt subjective specification of the features. And I think he's about right. And so that's almost an impossible thing to do, though. So got to do something. So this question just is not posed right. And so what the Bayesians are arguing about is how far, what is the distance that needs to be before you're willing to reject the goal? And nobody's agreed on that. So let's come back around, talk about this, we'll look at some alternatives, and then I'll show you I'll just say some other aspects of base factor calculations and what you need to be aware of when you count these things. So that's it for now, guys. Enjoy the weekend.